All right, I hope your day is going well and that you're excited to learn some math. Today, we're going to do a skill we're going to be using all year long. We want to be able to transform, which means to change in certain ways, 7 parent functions that we already know using the general equation a times f of x minus h plus k, where f of x is some function we already know. Specifically, we'll be focusing on the seven parent functions. And at the end of the day, you should be able to very easily find the equations of graphs like this, all sorts of different graphs, and be able to graph crazy things like this. Again, this is something we'll be using all year, so you want to be pretty good at it. Before we can get into this, you need to be fairly good at graphing the parent functions. So we're going to take a longer warm-up than usual. And what you're going to do is for each one of these parent functions, we've got y equals x squared, y equals x cubed, square root parent function, the cube root parent function, an exponential parent function, and an absolute value parent function. And for each of these, you want to be able to graph it with the exact points on there. So to aid you with that, you're going to fill out a table. So you're going to create a table and then graph the points. So you're using you're putting in different values of x that I've provided for you and filling out the table and then using that to graph. So take a few minutes and do this, and we'll go over them. All right, hopefully you did a great job with the graph of y equals x, the linear parent function. When x is -2, it says that the y will just equal -2. So y is -2. When x is -1, y equals -1. When x is 0, y is 0. When x is 1, y is 1. And when x is 2, y is 2. These points on the graph, when x is -2, y is -2. When x is -1, y is -1. When x is 0, y is 0. When x is 1, y is 1. And when x is 2, y is 2. This is a continuous graph. We could put in x equals 0.5 and get out y equals 0.5. And so we're going to connect it to show that all those in-between values exist. And we're going to put arrows on the end because there's no reason we couldn't put in a bigger x value and a smaller x value. So here's the linear parent function. You should be aware that it has a slope of 1 and goes through its key point. Its y-intercept in this case is 0, 0. Okay. The quadratic parent function, go ahead and fill out that table. And let's see if you got it right. When x is -2, -2 squared, -2 times -2, and negative times a negative is a positive. -1 times -1 is a positive 1. 0 squared is 0. 1 times 1 is 1. And 2 times 2 is 4. Oops, 2 times 2 is 4. So when we put in each of these x values in for x, these are the y values we get out. When x is -2, y is 4. When x is -1, y is 1. When x is 0, y is 0. When x is 1, y is 1. And when x is 2, y is 4. Similar to the linear function, this is continuous. I could put in x equals 1/2 and get out 1/4, and all of the in-between values will make sense here, are defined. And so we're going to connect it. And we've got this nice quadratic graph making a parabola. Our key point here is going to be this vertex, which is at 0, 0. Okay, x cubed. Go ahead and make the table, make the graph, see how you did. When x equals -2, you should have gotten y equals -8. That's because -2 cubed means -2 times -2 times -2. -2 times -2 is +4. +4 times -2 is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 times 2 times 2 is 8. So these points on the graph are -2, 8. Well, that's way up there. -1. Oh, sorry, that's wrong. -2, -8. That's way down here. -1, -1. 0, 0. 1, 1. And 2, 8. And it makes this graph that looks like this. The things we should be familiar with are, of course, that it has this key point, this is the inflection point. It's where it changes from being concave down to concave up. The bend is changing, even though it's increasing on both sides of it. So the function continues to increase, but it changes from concave down to concave up at 0, 0. That's going to be the key point we're going to use. The square root of x, go ahead and make this table, fill out this table, and make the graph. We'll see how you did. All right, when x is -4, the square root of -4 is imaginary. It is undefined. There is no number times itself that gives you a negative. No real number, at least, that gives you a negative. And so we say the square root of a negative number is undefined. The square root of -1 is undefined. The square root of 0, what times what gives you 0? Well, 0 times 0 gives you 0. 1 times 1 gives you 1. What times what gives you 2? 2 times 2. Or what times what gives you 4? 2 times 2 gives you 4. And so we don't end up with any values over here because when we put in negative x values, all the values, the y values are undefined. So we don't end up with any graph over here. But we've got this point at 0, 0, 1, 1, and 4, 2. And we get this nice shape that has a vertex at 0, 0, and is concave down but increasing. So here's our square root graph, and our key point is again going to be at 0, 0. You may have noticed so far that all of our key points have been at 0, 0 so far. That's true for a lot of parent functions, but not for all of them. So let's be a little careful. All right, let's look at the cube root function. So what times what times what gives you the number you put in? So when x is -8, what times what times what gives you -8? The answer is -2. A negative times a negative times a negative will give you a negative. So unlike square root, which has undefined values for negatives, you could do the cube root of a negative. Cube root of -1 is -1, cube root of 0 is 0, cube root of 1 is 1, and the cube root of 8 is 2. So again, we're asking what number times itself 3 times will give you this number. So I'm not going to graph these -8, -2s because they don't really fit nicely, but I will graph -1, -1, 0, 0, 1, 1, and then we can tell that it's going to be like, okay, well, I'll go ahead and graph this part. It's going to be at like 8, 2, so it's going to grow pretty slowly here. Look something like this. And our key point is going to be here, similar to the cubic parent function. This is an inflection point, and it occurs at 0, 0. The function changes from being concave up to concave down. Okay, here's an interesting function, 2 to the x. Hopefully we remember our negative exponents. Go ahead and fill out this table. You should have gotten that when x is -2, 2 to the -2 power means 1 divided by 2 squared, so 1/4. 2 to the -1 power means 1 divided by 2. Anything to the 0 power is 1. 2 to the 1 power is 2. 2 squared is 4. This is an exponential function that has a constant multiplier of 2. And let's put on when x is -2, y is 1/4. When x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. And when x is 2, y is 4. This function makes this shape right here, and its distinctive features are the fact that it has this asymptote at y equals 0. The asymptote. And its key point, notice there is no point at 0, 0 in this parent function. Its key point is at 0, 1. Its y-intercept is its key point. So that's something to keep in mind for later today because this will act very differently than the other parent functions. Our last parent function is the absolute value of x. So when x is -2, the absolute value of -2 is +2. When x is -1, the absolute value of -1 is +1. Absolute value of 0 is 0, absolute value of 1 is 1, and the absolute value of 2 is 2. When x is -2, y is +2. When x is -1, y is +1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. And we get this nice V-shaped graph with 2 constant rates of change, one increasing, one decreasing. The key point here is the vertex at 0, 0, and we'll be making use of this today. So Hopefully we feel comfortable with all of these parent functions. We should know that linear functions make a straight line, quadratic functions make a parabola, cubic functions make this kind of wiggle shape where there's an inflection point. It kind of goes up, takes a break, and then keeps going up. Square root graphs are increasing but concave down, and they only have a graph on one side. Cube roots look a lot like a square root, but in the opposite direction. They have this negative square rooty looking guy going on here with an inflection point at 0, 0. Exponentials have this asymptote at y equals 0, and they decrease towards it and then increase the other way. They're concave up. And absolute value graphs make this V shape. So hopefully we're feeling good about this warm-up, and we feel good about where our parent functions are. We're going to be using them a lot today. So